Yeah, you're just gonna go eat candy because I was gonna know. Okay, as I was saying, I was lying to you because I was teaching you an older model of what acids and bases are. Now we've since updated our model, and we're going to update our model here in a second, but the old model that we just covered in the previous unit was that an acid is a chemical that ionizes in an aqueous solution to form hydrogen ions. Pick any acid, weak or strong. Doesn't matter. Pick any acid that you want.
Sulfuric acid.
Sulfuric acid. Let's choose sulfuric acid. Okay.
Oxygen acid.
H2SO4.
Isn't that sour gas?
What? Sour gas is H2S, right? Sour gas is H2S. So H2SO4, when you put this chemical in water, I mean it's already in water in order to be H2SO4, but when you put this chemical into water, what does it actually turn into? Turns into H positive, and what else? HSO4 what? Negative, right? If a neutral compound splits into a positive, then the other thing has to be a negative, right? Okay. Now that's incorrect. It does kind of do this, kind of a little bit, but it needs something. What has to happen in order for this to split up this into this and this? What do we have to add this thing to? What substance do we have to add this to in order to get it split up?
Water.
We have to add it to water. And that's going to create a really kind of interesting interpretation of what actually happens here in a second. Bases is pretty straightforward. Bases, as far as you're concerned, are always ionic what? Hydroxides. So pick any ionic, what ionic hydroxide do you want to talk about?
Lithium hydroxide.
Lithium, let's pick lithium hydroxide. When you put lithium hydroxide into water, it dissociates at least a little bit. I mean, this is very soluble, so it will mostly dissociate. But it will at least dissociate a little bit to make lithium and hydroxide. That's not really going to change a ton, okay? So for strong bases, that's not really going to change a ton. But now this is what we call the Arrhenius definition of an acid and a base. This is in the 1800s. How long ago was the 1800s? 200 years ago. We're using a model of acids and bases that's almost 200 years old. What he did is this is the old definition, and we're going to modify it a little bit. And the way that we're going to modify, we'll talk about it later. Sorry, we're going to modify it here in a little bit. Properties of acids and bases. Does anybody remember the properties of acids and bases? So they're both electrolytes, right? Because they both have ions, so they are both electrolytes. But what's something interesting about acids? Okay, they turn litmus. The litmus turns red. Likewise, bases turn litmus what color?
Blue.
All right. Litmus turns blue. Does anybody else know anything about acids at all? What? Yeah.
Sour or bitter?
They are. Which one?
Sour.
Yeah, acids.
Sour is acids and bases are bitter.
Good. They taste. Sour. I was trying to figure out how to spell sour. So if acids taste sour, what's the opposite of sour?
Bitter.
Good.
Sweet.
Ooh, I was hoping somebody wasn't going to say sweet.
Oh.
Bitter. Has anybody ever tasted soap before?
Yes.
Yeah, nobody. You've had your mouth rinsed out with soap before? Parents? No. That's a really common punishment, right? For if somebody has a potty mouth, I'll rinse your mouth out with soap. So soap tastes bitter, and that's because soap is a base. Yeah.
Bases are slippery and acids are sticky.
Oh. Bases. They feel slippery to the touch. And that's because bases can react with the fats and the oils on your skin, and they can make like a soapy kind of compound that allows your fingers to glide together really easily. Now, I don't know if acids are sticky necessarily, okay? So that's not necessarily true all the time, but all bases feel slippery. Acids are no more necessarily or less slippery than water, but acids do something. They do something. They react with metals sometimes to form hydrogen gas. And that's going to become important later on in the unit. And then finally, how would you describe quantitatively what an acid is using numbers? A pH of, we're not going to say 6 and under, we're just going to say less than 7. Do you guys know your less than and greater than signs? Uh-oh. Has a pH greater than 7. So is a pH of 7.5, is that acidic, neutral, or basic? Basic. It is technically basic. It's like the tiniest little bit basic. I would consider it to be neutral, but it is, by a textbook definition, it's basic. Toka, there's notes in the purple bin at the back of the class. Okay, so I just need to go over that. That's more of a review of Science 9 and 10 than anything. Okay, so acids make hydrogen ions. Ooh, okay, whatever. What the hell is a hydrogen ion? Let's take a look at a real in-depth picture of what a hydrogen ion is. How many protons are in H+? Do you remember how to figure out how many protons? Did we do this at the beginning of the semester? Yeah, we did. Okay, how many protons are in hydrogen? 1. Any hydrogen atom in the universe, by definition, it has 1 proton, right? What? This just totally not related to this. How many protons would, I don't know, manganese have? 25. If it's manganese, it has 25 protons. That's what makes it manganese, okay? How many neutrons does a hydrogen ion have? Keep in mind, its mass refers to the total sum of all of the protons and neutrons in it. So if it has a mass of, we're going to call it 1, right? Most of them have a mass of 1. So if it's got a mass of 1, and we know it has 1 proton, how many neutrons can it have? None. A hydrogen ion has no protons. Why? If let's say it had 1 neutron, what would be the mass of it? It'd be 2, but it doesn't have a mass of 2, it has a mass of 1, so it's 0. Okay? How many electrons?
0.
Less than 1.
So let's think about this. Normally in the Bohr model, right? Proton, it's got 1 proton, it's got 1 electron, right? And so its charge is 0 as an atom. But is this an atom? It's an ion. So have we gained or lost a negative? We lost 1 negative. So now how many electrons do we have? We have none. We have 0 electrons, 1 proton and 0 neutrons. So what could, if we wanted to use a different name other than a hydrogen ion, what would we call this hydrogen ion? We would call it a proton. This is a bare proton all by its lonesome self. Not interacting necessarily with any electrons, not interacting necessarily with any neutrons. This is a proton all by itself. So we call hydrogen ions, I will now, from now on, be calling hydrogen ions protons. So a hydrogen ion equals a proton. And it's really weird to think of a bare proton all by itself, but that's exactly what it is. And so because this is a single positive charge all by itself, it behaves really interestingly. It behaves really uniquely, okay? Here, do you know what substance all of these things are? Sure looks like H2O, right? And so if I popped a proton right smack dab in the middle of this solution, right? When I add an acid, adding an acid is a lot like adding hydrogen ions or protons. Now, this proton, it's not going to survive all by itself very long. This proton is one bare, empty, naked positive charge. And so that naked positive charge, it really, really, really is attracted to anything surrounding it that's negative. And we haven't really gone over this a ton, but water molecules are polar. They have positive sides and negative sides to them. Did we talk about that in our solutions unit a little bit? Yeah. So water has a negative side to it, and this water will attract the positive. And so if the water attracts the positive, and if they get bound to each other, all of a sudden, how many hydrogens are on this water molecule? 3. And so we're going to name this ion something else, okay? So there is no evidence to suggest that these protons just float around all by themselves. In reality, what happens, I'm going to go back, you don't have to go back. In reality, what happens is this proton actually hops from water molecule to water molecule. It's constantly hopping from one to the other, okay? That's the idea that I want you to get of an acid, is a proton that's constantly hopping from one water molecule to the other. So there is no evidence to suggest that these protons are just all by themselves. Instead, we get the following reaction. So we get H plus H2O. Well, when we smack these things together, what are we going to get?
H3O.
We're going to get H3O. What? What kind of a charge is it going to have? When you add a positive to a neutral substance, you get a positive. And this thing is going to be aqueous. This is what we call hydronium. Hydronium is a brand new ion that you've never seen before, but you have actually seen it before. You've totally seen it before. Have you ever seen hydronium before?
No.
Yeah. You've seen it on your table of acids and bases. Look for hydronium on your table of acids and bases. So look for it's the shaded one, right? So hydronium is H3O plus. Now, I want to be very clear. Hydronium is the strongest acid that can possibly exist in water. Remember, if you put a stronger acid than hydronium, right? All of these 6 acids are strong acids, right? So the moment we put any of these in water, they immediately turn into what? that thing and a hydrogen ion. But remember, a hydrogen ion, the moment you add it to water, what does it actually turn into? It's a proton, and when the proton reacts with water, it turns into hydronium. This is a really, really, really interesting kind of conclusion that we were able to get from this. So the modified definition. This is still Arrhenius's definition, but we're going to modify it a little bit. So an acid is a substance that creates hydronium when reacted with water. We're now no longer considering hydrogen ions to be the basis of an acid. Now it's a hydronium ion. And that's what we call the modified definition of an Arrhenius acid. So, by way of an example, when you add HCl to water, normally, when we would add HCl to water, the hydrogen would just pop off. Would you agree?
Yeah.
But now, when the hydrogen pops off, the hydrogen ion or that proton is immediately attracted by water. So you can think of the hydrogen as being transferred from the hydrogen chloride to the water. So what are we going to get here? We're going to get chloride ions and hydronium. Every time you think hydronium, you're really thinking water with a proton attached to it, and the proton is hopping from one water molecule to the next, the next, the next, the next, the next. Now that's a big conclusion to reach. That's a huge shift in our perspective of what's actually happening at the microscopic level, or at the atomic level, or molecular level. Okay, let's keep going. So when hydronium and hydroxide react, what would they create? Let's think about this. Hydronium, what types of substances make hydronium? But what classification of substances? Do neutral molecular substances make hydronium? No. Acids make hydronium, right? So this is like saying when acids and bases react, what do they make? Do you remember what acids and bases make when they react? They make a neutral substance. Well, let's see if they make a neutral substance. Let's try this. Hydronium, what's the formula for hydronium? H3O plus aqueous. And when it reacts with hydroxide, what's the formula for hydroxide? OH minus aqueous. What's going to happen here, do you think? The H is going to transfer from the acid to the base. This extra proton, remember that proton is hopping from one water molecule to the other. So this proton can hop from the hydronium to the hydroxide. So what are we going to get? We're going to get H2O plus what? OH2 or H2O. Would you agree when acids react with bases, we get neutral compounds? We get these water molecules. Again, I really do want us to focus on what the picture is going to say, right? So it's really important that we kind of are able to visualize this. So what does a hydronium look like? Jana, sorry. No, if you have to go, then you have to go, right? What does hydronium look like to you? What do you think it's going to look like? How many H's and how many O's? 3 H's surrounding 1 O, right? So I'm going to draw 3 H's. I'm just using, if anybody knows their models of the atom, the Dalton, the billiard ball model of the atom, I'm just showing them as balls, right? So this is 3 H's and an O, and this is positively charged. And it's going to react with, well, what does a hydroxide look like? It's OH. So it's another O and 1 H. And it's negatively charged. And what's going to happen here? What happens between the hydronium and the hydroxide? What is getting transferred from one to the other? A proton, a single hydrogen ion. So this proton will be transferred from one to the other. And so we get a water molecule and we get another water molecule. Now you might think, yeah, okay, Walton, I get it, no problem, whatever. But this idea, this way of visualizing chemical reactions is really powerful for us. This idea of protons being able to get transferred from one thing to another is going to become really powerful for us later on in the semester. Later on. What do we got? We got 7 minutes left. We got 8 minutes, but that's fine. We got 7 minutes left. What I want you to do, or what I want you to remember, is let's do a pH scale. Let's draw a pH scale at the top here. And what goes in the middle of your pH scale? The number 7. And how far down does the pH scale go? What's the lowest number on the pH scale? How far does it go? This pH scale technically goes on forever. There is no lower boundary to pHs. There is no upper boundary to pHs. I want to be very clear about that. It's almost impossible to get certain pHs, right? But I've worked with, personally in my lifetime, I've worked with compounds that had a negative pH. That were pH negative 0.8 was, I think, the lowest pH I ever dealt with in my entire life. And then I've worked with compounds that were, or solutions that were a pH of 14.9, I think was the highest pH I've ever worked with. So while I understand, yes, we do write typically from 0 to 14 or something like that, I need you to understand, thank you. I need you to understand that this scale does not end. You just put that stuff right. The scale does not end. It keeps going and going and going and going. Okay, where are bases on this pH scale? So these are bases. Where are acids? These are acids. And right smack dab in the middle, right? This is neutral. Right there. Okay, so what we want to know, in a neutral solution of water, we want to know, okay, how much hydronium is actually existing in water. And do you remember when I said, does water conduct electricity? And what was my answer to that? My answer was everything conducts electricity, right? Because everything is at least a little bit conductive. But there's a very good reason why water is conductive, is that's because water, what's the formula for pure water? H2O. Does it have any ions in it?
You mean?
Does it have any ions in it?
No.
No. Even at for pure water, I'm going to use this a lot over the next few days or a few weeks. Have you ever seen me use square brackets for a substance before? Does anybody know what this means? This means concentration of hydronium. Even in pure water, the concentration of hydronium, it's small, but there's hydronium in there. It's 1 times 10 to the negative 7 moles per liter. Why? Why in pure water? Sorry, Norlin. I don't know if there's a notes package in the back. Okay. What? In pure water, there's hydronium. Why? That doesn't make any sense. It's supposed to be pure water, right? There should be no hydronium in it. Remember, what's our vision of water? What's our vision of an acidic solution? Do you remember what I was trying to get you to kind of envision over here? What's actually happening to this picture? Ishi? What's happening? What's happening? What's happening? The proton is bouncing from one water molecule to another, right? And that's happening even if there are no acids in here. Are there protons attached to this water molecule? Are there hydrogens attached to this water molecule? Does this water molecule have hydrogens attached to it? Yes. Every once in a while, if you give this solution, this water, a little bit of energy, a hydrogen will just pop off. And the hydrogen will pop off of this thing here, and it'll start to bounce around from these solutions until it gets back to the original molecule, until another hydrogen gets back to the original molecule. So let's write that out, and that's going to be the last thing we really kind of take a look at today. This is called the autoionization of water. What we can do is we can think of two water molecules. If you give this solution or this mixture of water, I guess pure, but if you give this water a little bit of energy, let's say room temperature, then one of these hydrogens can pop off of this water molecule and it can hop onto the next one. What are we going to get when we get that happening?
And
We're going to get this water molecule turns into a hydronium, right? Because it turns into H3O plus. And what are we going to be left with when we're going to be left with a hydroxide. Water does this all the time. Do you think it does this more when it's hot or more when it's cold? Do you think if you gave it more energy, would this process happen more or less? More energy. The hotter the water is, the more this process takes place. Because those hydrogen ions have more energy to leave their water molecules. And so this happens all the time, and we're going to use this idea to kind of try and understand the pH system a little bit more than we have already. So I apologize. I know that was a lot. I get that. That was just a lot of you listening to me talk and stuff like that. Bring your calculators tomorrow, please. I know we just finished the unit where you need them, but definitely bring your calculators for tomorrow.